Okay, in the last video, we looked at the comparison test as one way to determine the convergence or divergence of different series. But we finished by looking at this series right here, 1 over 4 to the n minus 3. And just because of the way it's set up, in this case, because of the negative 3, the comparison test just doesn't work as a nice way to determine convergence or divergence. So we have another type of comparison test. It's called the limit comparison test. And I do actually stress at this point, you'll now have the comparison test, the limit comparison test, the nth term test for divergence, the integral test, as well as your knowledge of telescoping series, p-series, and geometric series. And ultimately, when you do your homework and when you do the exam, you're going to need to be able to list out each test as you do it. I'm not going to have you list them all out like on a blank page or something. But for each problem, when you're determining convergence, you're going to have to say, okay, I am using the integral test. Here are the conditions. Here's my integral. Here's my solution. Here's my conclusion. Oh, now I'm using the comparison test. Here are my conditions. Here's my math to solve the problem. Here's my conclusion. And you need to write out everything correctly. We've talked repeatedly about mathematical rigor and making sure you write everything accurately and correctly and formally. So just keep that in mind as we go through all these tests. You need to know all of them and be able to work with all of them. So here, if the limit comparison test, if you have two series that are positive term series, just like with the comparison test, they have to have positive values, and the limit as n approaches infinity of a sub n over b sub n is equal to k, where k is positive and finite, and that finite is important. The limit of a sub n over b sub n can't be infinity. It's got to be positive, which means 0 doesn't work, and finite. Then either both converge or both diverge. So the idea is similar to the comparison test. You want to know the convergence of a series like this, so you find another series that you already know the convergence or divergence of. Then you take the limit of the ratio of the terms of the sequences, plural, and they either both converge or both diverge together. So here, with the comparison test, we couldn't use 1 over 4 to the n because it didn't fulfill the requirements for the comparison test. But clearly, this series is essentially 1 over 4 to the n. Now, with the limit comparison test, I can use that. So my two series will be 1 over 4 to the n minus 3 and 1 over 4 to the n. That's geometric, and it clearly converges. Now, I look at the ratio of the terms. So I get 1 over 4 to the n minus 3 over 1 over 4 to the n. Now I take the limit as n approaches infinity. That's a fraction over a fraction. All of you can do the algebra. That's the limit as n approaches infinity. 4 to the n minus 3 goes to the bottom. 4 to the n goes on top. And I get 4 to the n over 4 to the n minus 3. Now there's probably different ways you could actually solve this. You could use L'Hopital. You can use 100 different ways. To make it really easy, I'm going to do a similar trick to the trick you all know from polynomial rational functions. Divide everything by 4 to the n. You get the limit as n approaches infinity of 4 to the n over 4 to the n over 4 to the n over 4 to the n minus 3 over 4 to the n. Now that becomes 1 over 1 minus 3 over 4 to the n. If you take the limit as n approaches infinity, this becomes 3 over infinity, so this goes to 0, and you get 1 over 1, which is 1. That tells me my k is equal to 1. It's positive and finite, which means either both series converge or diverge. Since we know this one converges because it's geometric, this one converges. All things being equal, this test is similar to the comparison test, but it's somewhat easier to work with because you're used to taking limits. So just taking the limit of the fraction, occasionally we can turn it to a function and apply L'Hopital, but most of them, you know algebra tricks to find the limits quickly. So in the past, students have preferred this to the comparison test, but I suppose that's personal preference. let's see. Another example. Maybe we can make this one messed up. Suppose I have the series n cubed plus n over 5 to the n cubed. And now, from a student perspective, this can be a little bit messed up to look at because it's got, it's got a cubic and a linear on top, a cubic and exponential on the bottom. And determining if it converges or diverges, just looking at it, can be somewhat tricky. And then trying to come up with something to compare it to can also be tricky. But like I said with the regular comparison test, don't put a lot of thought into this. It's actually pretty straightforward and simple. If we look at it, on the top, ultimately, the term that dominates is the cubic. On the bottom, the term, and give me 1 second, my video just moved, because as I mentioned in my live Zoom sessions, the only thing I have to use as a tripod for my iPad to video this is my cat tower, and one of my cats just leaped off of the top of the tower across the living room because he's chasing a bird outside now. Fantastic, through the window. So now, it shakes around when he does that. But ultimately, this is cubic on top. That's what matters the most. On the bottom, you have an exponential and a cubic. So use those as the series you're going to compare it to. So I'm going to compare it to n cubed, because that's what matters on top, and 5 to the n cubed, because both of those matter on the bottom. Now, clearly, I can simplify this to the series, the n cubes cancel, 1 over 5 to the n. This is geometric, the ratio is 1/5, so clearly it will converge. Now I can apply the limit comparison test, and as long as I get a k that's positive and finite, since I know this one converges, I can tell that that one converges. So I set up my ratio, a sub n over b sub n, which for us is n cubed plus n over 5 to the n cubed over 1 over 5 to the n. And now I'm just going to erase this a little bit so that we have more room because my whiteboard is somewhat small. Rearrange this, you all know the algebra. 5 to the n goes to the top, 5 to the n cubed goes to the bottom. And I get 5 to the n cubed plus n over 5 to the n cubed. The 5 to the n's cancel, and I get n cubed plus n over n cubed. And now, there's probably different ways to take this limit. The easiest, since there's one term on the bottom, break it up as two fractions. You get n cubed over n cubed plus n over n cubed, which is 1 plus 1 over n squared. Now if I take the limit as n approaches infinity, that's 1 over infinity. That becomes 0. And the limit's equal to 1. That's my k. It's clearly positive and finite, which means since this series, 1 over 5 to the n converges, this series, the one I actually care about, n cubed plus n over 5 to the n cubed, also converges. As far as it goes, like I said, students seem to prefer this test to the regular comparison test because taking the limits is pretty straightforward, and you don't have to worry about making your denominator bigger, smaller, and getting all the algebra correct. You can pretty much just look at something and say, okay, ultimately that's a cubic, exponential cubic. There's the series I compare it to. Simplify, get my convergence or divergence here, plug in limit, do algebra, and done. So it removes some of the thought for the series you have to come up with. So again, now you have the limit comparison test, the comparison test, the integral test, tests for p-series, geometric series, telescoping series, and the nth term test for divergence. You need to know all of them and be able to work with all of them correctly. And then in the next video I do, we'll look at another test. We have about 3 more that we want to go over, and then we'll kind of mess around from there.